Okay, ladies and gentlemen, we are busy with the chapter on forced convection, internal forced convection, and we are going to do a problem today, which is going to be problem 07, 2016. So on last year there were 5 additional problems that I've uploaded onto YouTube. Some of them were worked out on a yellow piece of paper, because at that stage I wasn't on campus when the videos were made. So please see them as supplementary to the work that we are doing now. I think they are of great value, and I would really recommend that you also look at them. But not only go and look at them, but start the video, look at the problem, work it out yourself, and then look at the solution. Okay? So, did you already start, Tamron? Okay, so you're rolling. Okay, so let's continue with problem 7, 2016. Okay, so this problem is related to some of you who have worked in the heating, ventilation and air conditioning industry, the HVAC industry, or some of you who are going to work there, and that is a duct. And the dimensions of the duct is, I'm going to give it to you just now, that is 200 millimeters, and that is 600 millimeters. Okay, and air that has been cooled to a temperature of 10 degrees Celsius is flowing through this duct, and the volume flow rate of the air is equal to 0.15 cubic meters per second. Okay. And this duct is 40 meters long. So it's a very long duct. Where will you get that? Well, you'll get it in buildings, in the attics, etc., into the ceilings. And because it is in the top part of building, or the upper parts, all the hot air obviously rises, and it collects there. And the temperature there can typically be 40 degrees Celsius, and in some cases even higher. So it is 40 meters in length. It's quite a long one. And around it, the air is at the temperature of 40 degrees Celsius. So we can assume that the duct surface temperature is 40 degrees Celsius everywhere. So what we have to do is to determine the outlet temperature and to determine the heat transfer rate, how much heat losses will there be through the duct, the pressure drop, and also the pump or the fan power required to move the air through this duct of 40 meters in length. Okay. So the cross-sectional area of the duct is something like this, 600 millimeters in that direction and 200 millimeters in that direction. Do you all understand the problem? Duct, 200 by 600, 40 meters in length, air at the inner temperature of 10 degrees Celsius, that is the volume flow rate of 0.15 cubic meters per second. The surface temperature is 40. Who of you would like to guess what that outlet temperature is going to be? 40? Okay, somebody guessed 40. Somebody that would guess 10. No change in temperature? Nobody? Okay, so all of you agree that the temperature is at least going to increase. I've got 40 here. Anybody else for 30? There's a 30, a 35, 20. Okay, right. So we don't know. Okay, so it immediately, when we start these types of problems, we want to get the bulk temperature, because that's the temperature where we need the properties. And the bulk temperature, as you know, is the outlet temperature minus the inlet temperature divided by 2. Outlet temperature plus the inlet temperature divided 2, the average of the two. We've got the inlet temperature as 10, but we do not have the outlet temperature. Okay. So what I'm going to do is I'm going to select 15. Okay, 15, because I'm going to choose maybe an outlet temperature there of 20. So 20 plus 10 is 30, divided by 2 is 15. That was just my selection. You can choose whatever you want, and at the end of the problem I'm going to show you the sensitivity of your selection on the problem. Okay. So at that temperature, in table A15 in your textbook, you can get the properties of air, or you can get it anywhere else you want. And the properties of air would be the following: 1.209 kilograms per cubic meters for the density, that is then at 15 degrees Celsius. The CP value is 1004 joules per kilogram Kelvin. K is equal to 0.02476 watts per meter Kelvin. The Prandtl number is equal to 0.7305, and the viscosity is equal to 1.802 multiplied by 10 to the minus 5 kilograms meters per second. Right, density 1.209, CP 1004, the K value 0.02476, the Prandtl 0.73, the viscosity 1.802 multiplied by 10 to the minus 5. If you go and look at your textbook at 15 degrees Celsius and at that temperature the values are given, you'll see my values are not exactly the same as in the textbook. What's the reason for that? The reason is that in your textbook, Cengel and Ghajar, there's actually a CD-ROM or something in it with the program EASE on, EES. Okay. And it's a very helpful tool in the sense that in that you can just specify rho for air at that temperature and it will calculate all the values for you. And you can also select from which database it must calculate the values. So it saves you a lot of time in terms of interpolation. Okay. So I like to make use of this program for this, and I also use it a lot for my normal calculations. Some of you might also find it very helpful with your designs if you make use of this program. It's a very simple program. Right. Now, let's also just look at other things that we are going to maybe need. The cross-sectional area. The cross-sectional area, in this case, would be equal to 0.6 multiplied by 0.2, which is equal to 0.12 square meters. That's a cross-sectional area. The surface area for heat transfer. The surface area for heat transfer would be this outer surface. Okay, so it is the perimeter multiplied by the length. Okay. So it's the perimeter multiplied by the length. Our perimeter in this case is equal to 0.2 plus 0.6 plus 0.2 plus 0.6. Okay. So it is 2 times 0.6 plus 0.2 multiplied by the length, which is 40 meters. The perimeter, 0.6 plus 0.2, 2 times, multiplied by the length, is 40 meters. And from that we can get the surface area as 64 square meters. Now take note of the geometry. It's not a circular tube. And the equations of Glinsky, Sider and Tate, because we're going to later on calculate the heat transfer coefficient, and also the Reynolds number, is based on a circular tube. And this is not a circular tube. So we need to change this tube to that of a circular tube, and we do that by using the hydraulic diameter. So the hydraulic diameter is equal to 4 times the cross-sectional area divided by the wetted perimeter. 4 times the cross-sectional area divided by the wetted perimeter. So that would be where the air will be in contact with the surface. Okay, we've got 4 times the cross-sectional area is 0.2. The perimeter is 2 times 0.2 plus 0.6. So 0.2 plus 0.6 is 0.8 multiplied by 2 is 1.6 meters, and the hydraulic diameter works out as 300 millimeters. So it means that this tube, we are going to consider it as if it is a tube with a diameter of 0.3 and a length of 40 meters. The volume flow rate has been given, and we know later on we're going to need the mass flow rate or the velocity. So let's just calculate the velocity of the air through the tube. The volume flow rate would be equal to the velocity multiplied by the cross-sectional area. The volume flow rate has been given as 0.5 cubic meters per second. It's equal to the velocity divided by the cross-sectional area, which is equal to 0.12, and from that we can calculate that the velocity would be 1.25 meters per second. The air velocity, 1.25 meters per second. The mass flow rate is equal to rho multiplied by the volume flow rate, or it is equal to rho v multiplied by the cross-sectional area, however you want to calculate it. So in this case, I'm going to do it like that. The density is equal to 1.209 multiplied by the volume flow rate, which is equal to 0.15, and the mass flow rate is equal to 0.1814 kilograms per second. Okay. Ladies and gentlemen, am I going too fast? Can you stay with me? Is the pace okay? Okay. Next thing, the Reynolds number. We want to know if the flow is laminar or turbulent, because that determines how long it is going to take to fully develop. So that is an important thing. The Reynolds number is equal to rho v d divided by the viscosity. Okay. And actually this d is the characteristic length. Okay. And for this case now, we work with the hydraulic diameter. So our Reynolds number is based on the hydraulic diameter. I'm not very good in many cases to do this, but I suppose it would be a good discipline to always work it in. The density is equal to 1.209. The velocity we've calculated as 1.25. The hydraulic diameter is 0.3 divided by the viscosity, which is equal to 1.802 multiplied by 10 to the minus 5. And that gives us a Reynolds number of 25,167. 25,167. Transition occurs at about a Reynolds number of 2,100 to 2,300 for a circular tube. We've made this thing a circular tube. It's not a circular tube, but we've made it one. Okay. But the Reynolds number is far more than 10,000 also, so it is fully turbulent flow that we're talking of. Okay, turbulent flow. Therefore, because it's turbulent flow, how long will it take to be fully developed? It would be 10 times the hydraulic diameter. Okay, so it is 3 meters. Okay. 3 meters that it will take. So, schematically, if we look at this long duct of 40 meters, okay, 3 meters typically on a scale would be something like that. So, in that area, the heat transfer coefficient will be higher. Here it will be fully developed. So, we're going to make the engineering assumption that that is not so important, that first part. We can consider the tube as if it is a fully developed tube. Understand? So it's a discretion that you take, it's an assumption that you're going to make in terms of the specific problem. Right, now let's calculate the Nusselt number. So the Nusselt number is equal, and again it is now based on the hydraulic diameter, is equal to the heat transfer coefficient multiplied by the characteristic length. The characteristic length is the diameter of the tube, dH, the hydraulic diameter divided by K. Okay, and that is equal to, and I'm going to use again the Dieters-Boulter equation. With the previous lecture, we've looked at all the equations which are available, and we've discussed the selection of these equations. Why do I choose the Dieters and Boulter equation? Because I'm lazy. Okay, it's the easiest one to calculate. So it is equal to 0.023, Reynolds to the 0.8, Prandtl to the 0.4. Okay. This equation is actually Prandtl to the n. Okay. And with the n, you have to make a selection. If the fluid is being cooled, then n is equal to 0.3. If it is being heated, like in this case, because of the warmer surface, the n would be equal to 0.4. Okay, so that's the reason for the 0.4. So let's calculate the Nusselt number. That is equal to 0.023. We have the Reynolds number now. We've calculated it as 25,167 to the 0.8 multiplied by the Prandtl number. There's the Prandtl number from the properties, equal to 0.7305 to the 0.4. The result is that the Nusselt number is equal to 67.27. There's our Nusselt number. But the Nusselt number, based on the hydraulic diameter, is equal to the heat transfer coefficient multiplied by the hydraulic diameter divided by K, as we've already written it there. We've got the Nusselt number now. It is 67.27. It's equal to the heat transfer coefficient multiplied by the hydraulic diameter, which is 300 millimeters or 0.3 meters, divided by the thermal conductivity of the fluid, which we have in terms of the properties, and that is equal to 0.2476. Okay. And therefore, from this, we can calculate the heat transfer coefficient as 5.553 watts per square meter degrees Celsius. Are you with me? Right, now let's calculate the heat transfer rate. So the heat transfer rate is now equal to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus T bulk. Okay. The heat transfer coefficient is equal to 5.553 multiplied by the surface area, which is 64, multiplied by the surface temperature, which is 40, minus the bulk temperature is 15, and that gives me the heat transfer rate of 8.86 kilowatts. And now I can go and calculate the outlet temperature of the air, MCP multiplied by the outlet temperature minus the inlet temperature. The heat transfer rate is equal to 8.86 multiplied by 10 to the 3. It's equal to the mass flow rate, is equal to 0.1814. Outlet temperature minus the inlet temperature of 10, and now we get the outlet temperature as 58.79 degrees Celsius. Oh, sorry. Forgot the CP. Yeah. CP 1004. Here. Oh.
You should use the law of temperature difference.
Aha, yes. Thank you. It's all wrong. It's a trap. It's the classical trap. I've spent theory, and I've explained to you why it is important that you cannot do it. You've got a constant world temperature, you need to use the LMTD. Otherwise, this is going to happen. Look at this outlet temperature. I mean, it can't even be. World temperature is 40. How is it possible? Even although I've made maybe a mistake here. So, ladies and gentlemen, this is all wrong. Okay. Very important. So, I believe in sketches. Okay. Because it really helps you. We have this problem, a wall which is a wall at 40 degrees Celsius. Okay? And this temperature is constant. So the temperature there is 40 and it remains to be 40. Right? The inlet temperature is 10 degrees. Okay. And my selection of the bulk temperature, I don't even know what this outlet temperature is, was 15. So there's the bulk temperature of 15. So I cannot use this delta T to calculate the heat transfer rate. I need the correct temperature difference, because with a constant wall temperature, you're going to get something like that. And we need this, we need to integrate this to get the correct delta T. That is why we need the LMTD and not the normal delta T. The normal delta T you can use for constant heat flux, where these two lines are parallel to each other, okay? But not for constant wall temperature problem. So, let's correct it. I would like to first also calculate the NTUs, the number of transfer units. It's equal to the heat transfer coefficient multiplied by the surface area divided by the mass flow rate, excuse me, and the CP. The heat transfer coefficient we've calculated as 5.553 multiplied by the surface area 64 divided by the mass flow rate is equal to 0.1814 multiplied by the CP, which is 1004, and this is equal to 1.952. 1.952. This thing tells me a lot. It tells me that that inlet temperature is going to change significantly. If it's a very small value, you can know that there will almost be no heat transfer. If it is 3, if it's about 3, then I would know that the outlet temperature is going to be 40. Okay. So for design purposes, in many cases, I designed for a value of 2. So even between 2 and 3, it's a big increase in length. Okay, but 2 is a good value, so this is close to 2. So it tells me that inlet temperature is going to change significantly. Let's check it. How do we calculate the outlet temperature? Well, with this equation that we've derived in the theory classes. Outlet temperature is equal to the surface temperature minus the surface temperature minus the inlet temperature, e to the minus NTU. In your textbook, they immediately use the heat transfer coefficient, the surface area, the mass flow rate, CP, etc. You do the calculation, but you do not get a feeling before the time for how good the heat transfer rate is going to be. Okay, so I prefer to do it like this. So the surface temperature is 40, the inlet temperature is 10, and the NTUs is equal to 1.952. So the outlet temperature is 40 minus 10 e to the minus 1.952, and that gives us an outlet temperature of 35.74 degrees Celsius. 35. Okay, so any HVAC engineer will get a heart attack. Something like that. Okay. Because, I mean, you spent a lot of money to cool the air to 10, and now it's going to increase in temperature to 35, and you do not want to put in a venue like this temperature at air at the temperature of 35 degrees Celsius. Question?
So why do you use the surface area of the rectangle and not the circular tube?
That's a good question. I will have to go and think about it, but I think you can do the circular tube also, and I think the surface areas will be the same. Ellen, you shake your head. It's okay. So they are different. I will have to go and think about it. Okay. Okay. So, but with the new what will NTU then be if you do it like that? 1.15. Okay. It would be interesting to do the calculation also with 1.15. Okay. If I think quickly, if I just think quickly in terms of the theory, remember in terms of the theory, the Nusselt numbers. If you look at this chapter very well in terms of where they describe all the equations that you can use for the Nusselt numbers, then they say you can use the hydraulic. It is an assumption, but to get the Nusselt numbers, you use the hydraulic diameter. Okay. To get the Nusselt numbers, you get the hydraulic diameter. But also the Nusselt numbers are based on the Nusselt numbers are also based on the Reynolds number, and the Reynolds number is also based on the hydraulic diameter. But if you think of this as this derivation that we did here, we worked with the area of the control volume. And I think that's the reason. So I think this is correct to use this area and not that of the tube. So let me just go back and revisit this. So by doing this, okay, we can get a Reynolds number based on the hydraulic diameter, and then we can use that to get the Nusselt number based on the hydraulic diameter. So therefore, to get the heat transfer coefficient specifically. Okay, and for that reason also, with the surface area where we're going to calculate the heat transfer rate, we are going to use the surface area, not this surface area, but we're going to use that surface area. Okay, so I think that's the answer. Right, now, we've got that 35. Okay, so now we can calculate the LMTD. Okay, the LMTD. Take a good look at your sketch, and that is why I would recommend that you make a sketch. You've got those two temperatures, and you've got those two temperatures. You see? So, let's start by saying the LMTD is that temperature minus that temperature. Okay, that temperature difference. It is 40 minus 10. Minus this temperature difference. 40 minus 35.7, 35.74. Sorry. 40 minus 35.74. Is that right? Okay. So those two temperature differences divided by the ln of those two terms. Okay? And that is equal to 42.5. Okay? No. No. I've made a calculation error. Look at the sketch. Before the time, look at the sketch and just decide for yourself, what do you think will it be? I mean, that is 10 and that is 40. So it cannot be 30, isn't it? It cannot be higher than 30. It can't really be lower than about 5. Those are my two limits. So if you go and do the calculation, you must sort of know what to expect. It is equal to 13.19 degrees Celsius. Therefore, what does the LMTD mean? It means that if you take this temperature difference, that one, all of that, and you integrate that, and you divide it by the length, that area, and you divide it by the length, you get an average temperature difference like that. And that is my LMTD. It's a good representation of the average temperature difference between the two streams. 13.19. Right. Now, I can go and calculate the heat transfer rate. The heat transfer rate is the heat transfer coefficient multiplied by the surface area multiplied by the LMTD. Okay? That is the correct way of calculating the heat transfer rate if we've got constant wall temperature. It is equal to the heat transfer coefficient, which is equal to 5.553, multiplied by the surface area is 64, the LMTD, which is equal to 13.19, and that gives us a heat transfer rate of 4687 watts. Okay, it's not an engineering answer. That is 4.7 kilowatts. 4.7 kilowatts of heat. So no HVAC engineer would be happy with this. How would you prevent it? Obviously by putting insulation around the duct. Okay, putting insulation around the duct, and it can maybe be a good exam question for a problem like that, to do this calculation, and now giving you the thickness of insulation and ask you what thickness of insulation will you put around the duct to ensure that this doesn't happen. Okay, right. Now, we've calculated the heat transfer rate, we've calculated the outlet temperature. However, take a note, it's very easy to make mistakes in calculations. We've calculated the heat transfer rate with this equation, getting the heat transfer coefficient and the LMTD. But we've got that temperature, and we've got the mass flow rate of the air. So there's an alternative way of calculating the heat transfer rate, and that should be a good check. They should be the same. So we can also say the heat transfer rate is also equal to the mass flow rate of the air, the Cp of the air, the outlet temperature of the air minus the inlet temperature of the air. Okay. Well, believe me, if you go and put in all the values, you get exactly the same answer. 4.7 kilowatts. Okay. Which will give you confidence in your calculations. Okay. Now, are we finished with this problem? Well, for the test and exam, it would be fine, except that you need to write me something here. And what should that be? Okay. Remember, coming back to this problem, if we look at the beginning, I had to make an assumption for the bulk temperature. And what was my assumption based on? It was based on the fact that I said, I think the outlet temperature is going to be about 20. Now I'm quite surprised it is higher. So what do I need to do? I need to readjust, calculate a new bulk temperature and repeat all the calculations. What do you think will happen? Is it going to change the values a lot? Okay. So what we now need to do is we need to get the new bulk temperature, would be the inlet temperature and the outlet temperature divided by 2. Our inlet temperature is 10. Now we know our calculated bulk temperature is 35.74, although it was based on wrong values, which was not maybe that accurate, divided by 2, and that is 22.87. Now, based on this temperature, this bulk temperature, I read all the calculations. So I did go and get new properties at that temperature, which means that you will have to do a little bit of interpolation in your textbook, or you will have to select a temperature of 23, and I think even for that you will have to do linear interpolation. So you can go and get all the new properties for rho, k, etc. I'm not going to write them down for you. And then redo all the calculations. And if you do that, then the new Reynolds number is going to be 24,003. So it changes from 25,000 to 24,000. And the NTUs changes to 1.973. The outlet temperature changes to, guess what? 35.83 degrees Celsius. Previously we've said 35.74. Now we redid all the calculations and we get 35.83. It's a small change. The heat transfer rate, go and calculate the heat transfer rate, is equal to 4,581 watts. 4.6 kilowatts, 4.7 kilowatts. It's the same answer. And if you want to, you can now go and redo the calculation again. So you can say, hello, let's recalculate it again now for bulk temperature again of inlet plus outlet divided by 2, which is 10 plus 35.83 divided by 2. And if you go and redo all the calculations, then the heat transfer rate remains the same, 4,580 watts, or 4.6 kilowatts. Okay? So, but now you might say, well, yeah, okay, maybe it is because you've selected 15. What if I selected 10, or if I've selected 40? Because some of you can do that. We've done it previously. I'm going to show you the results for that also. So suppose you've done the calculations by selecting a bulk temperature of 10. Okay. Then the outlet temperature calculated would be 35.68 degrees Celsius. The heat transfer rate would be 4,758 watts. So you would get 4.8 kilowatts and not 4.5 or 4.6 kilowatts. Not that far out. Okay. Or let's suppose you've selected a temperature of 40, the other extreme, and you did the calculation. The results would have been an outlet temperature of 36.02 degrees Celsius and also a heat transfer rate of 4,365 watts, 4.4 kilowatts. Okay. Therefore, in the test and an exam, ladies and gentlemen, if you've done this calculation, you can just tell me, I have to redo it with a new bulk. It's fine, please, you do not have time, the test and exams, to redo the calculations, as long as you know how to do it. Any questions? Yep.
So does the material of the ducts contain a roll? Because we don't take that into consideration when we put out.
Yes, it is a good question. When does the material of the duct starts playing a role? We're going to do that in chapter 11, when we start looking at heat exchangers. Because what we have here is a duct, okay? And here we've got a temperature of 40, okay? And on the inside we've got the temperature now depending on where you are in here. That is the air temperature. But this problem is driven on what you've already done in the first few chapters in your textbook. Okay, by the three resistance terms. Okay. So the correct thing would be, in this case, is to take that temperature, to get the heat transfer coefficient up there, which we're going to do in the next chapter. The heat transfer coefficient for natural convection. You haven't done it yet. You can maybe in the meantime assume a value of 10. Okay. Then you can calculate that resistance, and then you can actually calculate that correct temperature there. Now let's suppose it is 38. Okay. What now normally happens with the material here is that normally these ducts are made from galvanized steel, galvanized plate, and they are very thin. So for this one, if you look at the resistance, then it is that term of delta X, and there's a K underneath, thermal conductivity. I can't remember the rest, but it's driven by those two terms. That one is very thin, and the K is very high. So the thermal resistance of that is negligible. So for all practical purposes, that temperature there on the inside would then be also 38. Okay. So it becomes a little bit more complicated, but we're going to get there. It's the same principle now with insulation. So if you want to insulate now this thing, this duct, okay, let me draw it here. Okay, so let's suppose here's the insulation material. Okay. And here's the air going through there. Then again, we've got the resistance terms there for the insulation material, for the galvanized steel or the plate, and then for the air. And these three resistance terms will determine the heat transfer rate. So, if you put insulation there, you want this resistance term to be very, very high. Because if the resistance is very high, then there can be no heat transfer through it. And that is the idea. But what you're also supposed to do is now with insulation material, you can also look at the heat transfer to the environment. And again, you have to put that resistance term up there also and calculate, take it into consideration. Okay. So that is actually the correct way, and we're on our way doing that. Something that I also want to mention now is that coming back to the Ditters-Boelter equation, our selection for that. Okay. My lazy selection. Okay. What if I've selected the Glinski equation calculating the heat transfer coefficient for the same problem? And I did that also. We're not going to write it all out, but I'm just going to show you the results. Okay. So if the heat transfer coefficient was calculated according to Glinski, okay, then we first need to get the friction factor. And the friction factor is from that Peterkoff equation, 0.79 the ln of the Reynolds number minus 1.64 to the minus 2. You remember that? Okay, because we're running out of time, I'm not going to put in the values, but then you can just see, you just have to put in the Reynolds number, we've got it, and then you can calculate the friction factor. And the friction factor is equal to 0.2468. Okay, there's a friction factor. I've done this on purpose. This value is incorrect. Okay. How do we know that? Okay. Well, what I always do is I always go and check on the Moody chart. The friction factor is a function of Reynolds number. There's it for laminar flow. This is for a smooth tube. For epsilon divided by d equal to 0. And there is for the rough tubes. So this Reynolds number, if you just go and check very quickly, then you'll see this value must be equal to 0.02468. Okay. So just go and check on a Moody chart if your calculation is approximately correct. Right, now we can calculate the pressure drop. The pressure drop through the tube. The pressure drop through the tube is equal to the friction factor multiplied by the length divided by the diameter, rho v squared divided by 2. And the friction factor, here it is, 0.02468. Let's put it in, 0.02468. The length of the tube is 40. The diameter, or the characteristic length, we use the hydraulic diameter, okay, 0.3. Again, the friction factor, just as the Nusselt number, can be based on the hydraulic diameter if it is not a circular tube. Okay, divided by the density, which is equal to 1.209, multiplied by the velocity. The velocity was 1.25. Square divided by 2, and that gives us a pressure drop of 12.43 pascals. Okay. 12.43 pascals. And then you can calculate the fan power required. That would be equal to the mass flow rate multiplied by the pressure drop divided by the density, or you can calculate it as the volume flow rate multiplied by the pressure drop. And that is equal to 1.865 watts. Okay, take note, that would not be the electricity consumption of the fan. That would be the amount of energy or power that has been transferred to the fluid. You have to take into consideration the efficiency of the fan. Ladies and gentlemen, any questions on this problem? If not, thank you very much.